SwayamPrabha. Digital India. Educated India.
We shall start our discussion today on this course on thermal engineering, and the topic that we shall discuss today is the combined first and second laws applied to processes. In this course, we shall be discussing about a few systems, in particular thermal systems. We shall discuss that to complete the cycle, whether it is a thermodynamic cycle or mechanical cycle, essentially in that particular system there will be a few processes. So, if we need to understand the performance of the system itself, then we also need to carefully study about the processes those are there in the system, rather the processes which will eventually complete the cycle, and we can determine the cycle efficiency. If we need to do so, we need to know the first and second laws. We have discussed about these two laws. So, today we shall see that if we combine these two laws and if we apply to the processes, perhaps we shall be in a position to map those processes in different thermodynamic planes, essentially to estimate different properties at the end of the process. Thereafter, we can calculate the energy transfer either into the system by heat or energy transfer from the system by work. So, you know that since we have already discussed about first and second laws, those we have recapitulated, because in this course we are not permitted to have a detailed discussion on this particular these two laws, because those are there in basic thermodynamics course, but we have discussed about, and knowing fully that in fact we can really recall whatever we have learned from our undergraduate course and from our previous lectures. Now, we are in a position to frame the combined first and second laws. In fact, we are in a position to frame a mathematical formulation for the combination of first and second laws. So, let us write here if we try to combine these two laws, then we that first should know whether we are going to combine these two laws for a closed system or if we are going to combine these two laws for the open system. Okay. I will discuss today that as I was talking about, if we are interested in the performance of the system, be it a mechanical system or whether it is a thermal system, first we need to know the processes which will eventually constitute the cycle, and by knowing the processes, their character, whether the process is a reversible process or it is a an irreversible process, whether the process is a constant volume process or it is a constant pressure process. So, by knowing all these things, we can map those processes in different thermodynamic planes, and then we can calculate the properties, unknown properties, and eventually we can calculate the energy. Essentially, you know that if we are in a process in quantifying the efficiency, so at the cost of the input energy, what is the output energy? So, that is whether it is in, I mean, we are looking at the work transfer by the system at the cost of the input energy, or at the cost of the work input to the system, what is the net energy that we are getting. So, first and second laws we have seen. You also have discussed about the most classical inequality that is deployed in thermodynamics, that is the classical inequality. So, from the classical from the Clausius inequality, the most important classical inequalities, one of the most important classical inequalities to be precise, deployed in thermodynamics, that is the Clausius inequality. So, we can write it that ds is greater equal to del cube by t, right. So, this is we have studied the equality sign is valid for the reversible process, whereas this inequality sign is applicable for the processes which are irreversible in nature. So, now we can write T ds equal greater equal to del cube. So, this is we can write from the second law. If we now use first law, then we can write for a closed system. So, we are writing now for a closed system. So, in this case we can write del cube equal to del u plus delta w. We have ignored the changes in kinetic and potential energy if we consider this equation is the first law of thermodynamics for the closed system. Okay. So, that if we now write this, then we are getting T ds equal to greater equal to du plus delta w, right. So, this is basically the equation. Now, so this is basically why you are doing so, because we shall be using, in fact, if we really do not know it, we will not be able to map several processes in thermodynamic planes. So, this is the combined first and second law for the closed system. This equation can also be written in a different from in different form, not different form, rather if we can try to write this equation, but using second law and property relation, still we can write it. So, we can also write this equation in this form, that T ds equal to du. This delta w, if the closed system contains a simple compressible pure substance, that is a substance in which the changes in pressure, volume and temperature are considered, rather the work done due to mechanical, electrical and magnetic effects are not considered. So, basically if it is a simple compressible pure substance, that is only the changes in P, V, T are considered, the effects stemming from the applied or induced electrical and magnetic interactions are not considered. So, if that is the case, then this is P dV. It is not necessary that this work, if we would like to write the work done by this quantity P dV, it is not necessary that the system has to be a closed system. Even when the system is open system, you know that, and the maybe there is flow into the system, but the displacement of the system boundary is is quasi static. If the displacement, if the work done focuses on the system boundary and the boundary moves quasi statically, that means the deviation from equilibrium is almost negligible. In that case, we still can write delta W is equal to P dV. So, this is TdS equal to, this is again the combined first and second law, but written in different form. See, you know that as I was talking about, we can write this equation by simply using second law and the property relation. By how? You know that we can write that del cube is less than equal to TdS, right. This is second law, and from the property relation we can write TdS is equal to du plus P dV. So, this is less than equal to du plus P dV. So, this is what we are getting from the second law and property relation, and this is what we got, you know that from the second law and property relation. So, you know that del cube, that this is TdS is greater or equal to du plus P dV, and here del cube is less than equal to TdS equal to du plus P dV. So, I can write it, erase it, I can write this is equal. So, this is du plus P dV. So, this is basically, you know that TdS equal to du plus P dV if we use only the equality sign. We also can get it from this, that TdS is equal to du plus P dV, that is the property relation. So, this is what we are getting from the combined first and second law, and this is what we are getting by using second law and property relation. What I told you in the last class, that you know that this TdS equal to du plus P dV, this equation is valid for any processes, but we should be careful in applying this equation for any processes. Why? If you would like to apply this equation for any processes, then the equation has to be integrated over reversible path, and the results of integration can be applied to any processes. So, that is very important, you know, point we should remember. So, this equation is valid for any general processes, but if we try to apply this equation for any general processes, you know that if it is reversible process, this is fine, right. So, but if you would like to apply it even for the reversible process that we have discussed in the last class. So, basically any process, this equation is valid for any processes. Only thing we should be careful that it should be integrated over reversible path, and the results of integration can be applied. So, this is all about. So, this is first, you know, combined first and second laws. So, I will be writing combined first and second law for the closed system. Okay. So, this is for the closed system. If we go to the next slide, if we write combined first and second laws for an open system, rather I am writing okay. So, this is the case. What we can write? This is very important. You know, in a similar way that we can write that TdS greater equal to del cube, right. Only thing, so this is the combined first and second law. In the previous case, we have used first law applied to the control mass system when we have replaced del q by du plus pdv. So, the first law, this particular expression del q will come from first law. If we try to write this del cube for the for the open system, you have seen that that I also have discussed about this particular aspect, that this U is the thermal energy for the non-flow system. That is the internal energy, not specific. This capital H is the thermal energy for the flow system. So, when the system is open, so that is there is a flow, the thermal energy is not the internal energy, the thermal energy is internal energy plus some energy which is required to maintain the flow in the presence of pressure. So, basically we will be writing this is dH plus or minus. So, this is very important, that this dH plus delta W. So, this is the first law. Now, just the difference is, instead of using U, we are writing in the this form where this H is enthalpy. So, again if the movement of the system boundary is the movement of the system boundary follows quasi statically or quasi in a quasi equilibrium process, the system boundary movement takes place, then still we can write this expression delta cube equal to dH plus pdv, right. So, that what we can write, that this is TdS dH plus what, this is pdv. So, dH plus delta W. So, this is dH plus delta W. So, this is the combined first and second law applied to the process executed by an open system. Similarly, again I can write this del cube is less than equal to TdS, and if we try to write the property relation that we know, that is dH minus VdP, right. So, this is what we know from the property relation. So, this is again the form of, so this is second law and the property relations. So, this is obtained by making use of second law and property relation, that is second TdS equation dH minus VdP. So, these are very important to understand. Now, if you look at carefully whether the combined first and second law, it is for the open system or closed system, that we are essentially obtaining some kind of some properties like internal energy, enthalpy which cannot be measured directly. We can measure volume pressure directly. So, volume pressure, temperature, these are also thermodynamic properties, but these can be measured, these properties can be measured directly, but if we look at these equations du and dH, these properties cannot be measured directly. What we can do, we can still write these equations in specific form, that TdS. So, just I am writing, if I write using different color. So, we can write this is T ds greater equal to dH plus delta W. So, this is similar, del cube T ds equal to dH minus VdP. Okay. If we go to the previous slide, still we can write this is T ds greater equal to du plus P dV. Okay. And this delta cube less than equal to T ds equal to du plus P dV. So, these are written in the specific forms. So, you know nothing special. Okay. So, now what I was talking about, that we have at least identified that by making use of the combined first and second law, or by making use of second law and property relations, we can at least describe processes, several processes, and we also can calculate the properties which cannot be measured directly. So, now what we shall be discussing today, that there are several processes in a system. I mean, when a system is running, you know, in a cyclic following cyclic processes. So, if we try to perform, you know, as I was talking about, if we try to measure the performance efficiency of the system, at least we need to identify several processes, those constitute together to form a cyclic process. So, you know that before I go to discuss about a few specific cases, so the combined first and second law, we could frame some mathematical formulation by making use of the combined first and second laws, also by making use of second law and the property relations. We shall be using these mathematical formulations essentially to calculate the properties at the end of several processes. Knowing these properties, numerical value of these properties, we shall be, you know, able to calculate the total energy, whether it is added to the system by heat or it is coming out from the system by work. And of course, if we can do so, we can easily calculate the efficiency. But I would like to discuss a few important issues. So, you know that slowly we are moving towards the, you know, different systems, that those are there in this course, you know, content. First of all, we shall start our discussion with power cycle. So, now whether it is a power cycle or any other cycles, maybe the cycle is a thermodynamic cycle, or if the cycle is not a thermodynamic cycle, but it is still a mechanical cycle. So, what we need to do? So, basically before going to apply the combined first and second law, the most important points someone should remember, you know, is to identify the processes. So, here I am discussing that whether someone is interested in calculating efficiency towards predicting the performance, essentially you need to go through certain procedures of calculating different properties, thermodynamic properties. So, I would like to discuss a few important points. Those points should help us to, you know, proceed systematically essentially to perform those processes. But the bottom line is we need to apply combined first and second law. Before applying this, you know, combined this, the first and second laws, we should know this. So, first point is Number 1, first is if we know the system. So, as I was talking about in the system, if the system is running through a cyclic process. So, there will be a few processes and those processes will constitute together to form the cyclic process. So, first of all we need to do is schematic depiction of the system. So, this is very important. So, this is schematic depiction of the system. So, if we can schematically identify the system, perhaps it will help us to identify several processes. Number 2, say for example, you know that I am talking about power plant, thermal power plant. If we can at least visualize, it is very difficult to identify, it is very difficult to trace all the components present in the thermal power plant, and those components are directly or indirectly associated with the performance of the plant. But at least if we can somehow schematically represent the major components and the cyclic process, then it will help us to calculate the efficiency. Number 2 is that what we need to do, identify, knowing the schematic depiction, then we need to identify what is the working substance. So, identification of the working substance. That is whether it is a pure substance like water or it is a gas or if it is air. Why? Because if it is the pure substance like water, then we can make use of the property tables to calculate properties. If it is an ideal gas, then we can use the ideal gas relationship to calculate properties. Number 3, we need to next know, we have identified, rather we have schematically depicted the system, we have identified the working substance, then we need to know whether the system is an open system or the closed system. So, to identify whether system is an open system or a closed system. Right. So, these are the things. Okay. Number 4, which is again important. So, already these 3 steps someone should remember to calculate the efficiency. So, what is 4? If we can identify if we identify the process system is open system, fine. If the system is not an open system, if it is a closed system, then after identifying it, we need to identify the processes, right. So, next task is what are the processes, and we need to map those processes in different thermodynamic planes. So, identification of processes and mapping them in different thermodynamic planes. So, this is number 4. Number 5, what is next? So, we should identify the processes and then we said we shall immediately map those processes in different thermodynamic planes. What are the different thermodynamic planes? It may be PV, it may be TS, it may be HS, it may be TV. So, depending on the system we can rather we have to map those processes in different thermodynamic planes. Next is we have to identify if any property is remaining constant or not. You know that I am underlining one important line over here, identification of processes. This particular task needs to know whether any particular property is remaining constant throughout the process or it is 0. So, this is very important. So, in a way identification of processes demands to know whether any particular property is remaining constant throughout the process or not. So, I am not writing that particular aspect. Next, what you need to do, if we could identify the processes and if we have mapped those processes in different thermodynamic planes, then what are the properties are known for the initial and final state. So, basically this is identification of properties which are known at the initial and final states. So, this is so basically you know that we have identified if any particular property is remaining constant. Say for example, if its temperature remaining constant, then this is an isothermal process. If the volume is remaining constant, this is a constant volume process. So, this is very important, that is why I have underlined this particular line, that identification of processes. So, basically to get it, at least someone should know any particular property or properties, I mean that will depend based on the system. So, basically to know whether any particular property is remaining constant throughout the process. If we know it, we can identify the process and then we can map the process in PV plane. Next task is identification of properties which are known at the initial and final state. See, you know that say I can give an example, if it is a pumping process. Now, in a power plant what is done, condensate which is collected from the condenser is pumped back to boiler. So, we need to identify properties which are known as the initial and final state. So, at the inlet to the pump, water temperature of water at the inlet to the pump, that condensate which is collected at the at the basin of the condenser. So, at the inlet and the outlet. So, basically the process is almost an isothermal process. So, we can identify what what is the temperature. Similarly, we also can calculate properties which are known at the initial and final states, right. So, we know that when water is pumped from the condenser pressure to the boiler pressure, then temperature is remaining almost constant. So, we know that in a pumping process the temperature is remaining constant. So, basically this is the property temperature which is remaining constant at the initial and final states. Number 6 is to identify the property which is to be calculated, right, which is to be calculated. So, this is 6. Number 7 is write down first and second laws for that particular process. So, as I talking about pumping process, we need to know what is the property we have to calculate, because we have to calculate the pressure at the outlet of the pump, knowing fully that the temperature is not going to be changed during the course of pumping process, and then we need to write down the first and second laws, combine first and second laws. So, 7 is first law and second law, 8 is write down combined first second laws, right. So, this is very important. So, yet there are a few more steps someone should know before attempting to calculate, or before attempting to identify the process and calculate the property which is to be calculated. Next is 9, write down the property relations. As I told you, the property relations are useful to calculate properties which are not directly measurable, right. So, accounting for that particular aspect, we can write this particular step 9. Number 10, what is number 10? That is the last point. Last point is, it's very important point. Last point is very much connected to the point which we have mentioned here, that is identification of the working substance. See, we can even write first law, second law, we have identified the property which is to be calculated. We are writing the combined first and second law. We are also writing the property relation. Why we are doing so? We are doing so to calculate the property which is not directly measurable or calculated. Now, we need to consult with property table or not. So, basically the last point is connected to point 2, because if this is the working substance is the pure substance like water, we can directly use the property tables to calculate other properties. If it is an ideal gas, then we have to use the ideal gas relationship to calculate the properties. So, basically I am writing to use the property table or to use the ideal gas relationship for the calculation of property. So, this is very important. So, this we can identify from this particular point that whether the working substance is a pure substance or it is an ideal gas. Okay. So, this is that why I have written so, because I could have directly started my discussion from the identification of several processes, but I have discussed this particular topic or particular aspect only to make you understand that we can use property table, or we can use ideal gas equations to calculate properties, but I mean it should not be random. So, we need to proceed systematically by knowing the steps, rather intermediate steps correctly. So, basically I mean these points which I have listed down over here will help you to proceed systematically in the right direction, knowing the intermediate steps correctly. Okay. So, now let us first discuss about one particular process. I will be discussing several processes. So, let us first discuss about one important process. So, that is the reversible constant volume process. So, if it is reversible constant volume process, then what would be the equations that we will be applying, and for then of course, if you would like to map the particular process in thermodynamic planes, then how can we do it. So, if we write first process number 1, that is reversible constant volume process. Reversible constant volume process. So, you know that we have to write first law, we have to write second law, and then we can write the combined first and second law, right. So, reversible constant volume process. So, first law. Now, we shall be writing all these the relevant equation for all these processes for a non-flow process. So, basically for a non-flow system. So, non-flow system. If we consider the system to be a non-flow system, and if we are applying whatever we have learned from today's class, let us first discuss this process first, and if time permits, we will go to the next one, otherwise we shall continue, we shall discuss in the next class. So, the reversible constant volume process, that the first law systematically, it is given, if we go to the, I mean the first one is not required, because already it is given. Let me write it more clearly. Reversible constant volume process and working substance is water. So, you know that if we now go to these steps which we have written few minutes back, first one is not required, second one is also not required, third one is also not required, because it is given a non-flow system. Fourth one is also not also required. So, fourth one is also not required, because identification of processes is not required, because it is given reversible constant volume process, non-flow system, working substance is given. So, now we can make use directly to the first law, write down first and second law, because we really do not, nothing is said about that okay it is given or which property is to be calculated. So, it is a generic discussion we are discussing. So, you know from point 1 to point 6 it is not required. So, straight away we can go to point 7, that is first law. If we write first law for the non-flow system and the working substance is water. So, this is del cube equal to del W plus delta W. So, this is the process. See, now question is non flow process, this delta W can be written PdV. So, this is equal to 0. Okay. So, for non flow process, non flow system and constant volume process. Non flow system, so if we consider the process is a quasi equilibrium process and the volume is constant, that is given. So, PdV delta W is equal to PdV and that is equal to 0. So, the change in volume is not there. So, this is equal to 0. So, we can write this delta cube in specific form, that is du. So, this is first law, right. So, you can understand the change in internal energy within the system is nothing but the amount of heat which is being added to the system. If heat is added to the system and the volume of the substance, the change in volume of the substance is 0, then the change in internal energy of the substance is nothing but the amount of heat which is being added to the system. Second law, what is second law? Second law is that we can write reversible process. So, we can write ds equal to delta q by T. So, this is ds equal to delta q by T. We have not used the inequality sign. Why? We have taken, rather we have accounted for this particular term, that is reversible process. So, this is ds equal to del cube. You know that, so what we can write? We can write in a specific form delta q equal to T ds, right. So, that we can write. So, what is q to S2 minus S1. So, basically if we integrate it, we can write ds equal to delta q by T. Therefore, we can write S2 minus S1 equal to integral 1 to 2 del q by T. This is exact differential, this is point function. So, we can write the change in entropy between the initial and final states is nothing but equal to the amount of heat is transferred to the system through that particular system boundary, where the T is the temperature of the system boundary. So, you know that second law is giving that change in entropy, which is nothing but the the integration of dq by T via reversible path, where T is the temperature of the system boundary through which heat is transferred to the system. Okay. So, now this is second law, and if we go to the 7, we have written combine first and second law. See, now for the reversible process, you know that combined first and second law does not give you any special equation. So, basically the next equation that I will be writing, that is the property relation, it is not an additional equation for the reversible processes. It may be an extra additional equation for the irreversible processes that we will discuss in the next class. So, basically if we write the property relation. So, property relation that is TdS equal to, I am writing in the specific form, that is du plus PdV, right. So, you know that this quantity equal to 0. So, basically TdS equal to du. So, this is the property relation, right. this is basically valid for any processes, but the process is reversible one, and I have told you initially that even if this equation is valid for any processes, the clue is before applying this equation to any processes, we have to integrate it over the reversible path, and the results of integration can be applied to any processes. But so long as the process is reversible, that is not an issue. So, that is what we could write. So, you know that for this particular process, reversible constant volume process, if the working substance is water, we have systematically derived the first law, we have written first law, second law and property relation. If the working substance is not water, if it is air, we shall discuss it again when we shall be discussing about different mechanical cycles, but for the time being. So, basically this is the first law, this is the second law, this is the property relation. You know that you can't say that this is an additional equation, this is essentially the equality of the combined first and second law, that is what you have seen. If we go back to the previous slide, so in this equation you can see that this is basically TdS equal to du plus PdV greater equal to. So, basically equality of this particular equation. So, this is essentially the TdS. So, this is the combined first and second law. If you eliminate this inequality sign, you are getting TdS equal to du plus PdV. So, if this is the equation, so this is the property relation that we have written. So, this is not an additional equation for the reversible processes. It may be an additional equation for the reversible processes, but this is not a case for the reversible one. So, this is something we have expressed. Now, quickly try to map the processes in different thermodynamic planes. So, let us map it in PV plane. So, if it is volume, it is pressure, so this is reversible constant volume process. So, if it is reversible constant volume process, so if it is PV, so I am using different color. So, this is okay, and say this is T equal to T1 and this is T equal to T2, right. So, this is T equal to T1 and this is T equal to T2. Say this is the process. So, this is 1, this is 2, right. So, maybe this is the process. We are supplying heat to the system, temperature increases, and this is reversible constant volume process. Volume does not change. So, V2 equal to V1, So, there V2 equal to V1, right. So, this is basically we have to map this process in different thermodynamic planes. So, maybe this is P2 and this is P1. So, this is P1, this is P2. You can see that pressure changes. If we try to map this particular process in TS plane, right. So, if it is TS plane, then what would be the process of constant volume? You know that this is TS plane. So, say this is temperature T1 and this is temperature T2. So, this is T1 and T2. You can understand that T1 is greater than T2 from this particular expression, and say this is P equal to P1, this is P equal to P2. I am assuming that you already have learned this PT, TV, PV diagrams from your basic thermodynamics course. So, that now the constant volume process, reversible constant volume process, that the process will be like this. So, this is 2 and this is 1, right. So, this is the reversible constant volume process, and for this particular process V2 equal to V1. reversible constant volume process, volume is remaining constant. Upon receiving heat, thermodynamic state is getting changed from 2 to from 1. So, pressure increases P2 to P1. So, here P1 is greater than P2, temperature T1 is greater than T2. This is quite normal that upon receiving heat, the state point is changing from state 2 to state 1, temperature increases, pressure also increases, but volume is remaining constant. So, this is all about the mapping a reversible constant volume process in these two thermodynamic planes. Now, if you would like to summarize today's lecture, we have discussed about the necessity of framing the mathematical formulation of the combined first and second laws, which will be applied to any processes. Having a little bit of discussion on this particular topic, we have moved to figure out a few points which will help us to calculate the performance or overall performance of the system, and we have listed down all these all these points, and these points are very much necessary before applying the combined first and second law to any particular process. And then we have taken one particular example, that if the process is a reversible constant volume process of a substance, the substance is water, and the process is occurring in a system which is a non-flow system. And then we could write the first law, second law, also the property relation. In fact, we also have discussed that the property relation for this particular category is not an additional equation, rather it is the equality of the combined first and second law. Then we have tried to map the processes, that particular process in PV and TV planes. With this, I would like to stop here today, and in the next class we shall continue our discussion on this particular topic, and again what we will be doing, we shall be identifying a few more processes for both flow and non-flow and flow, and then we shall try to map those processes in different thermodynamic planes. Thank you very much.